Hello, I'm Thomas Shukla. This is Physics 2212 at Georgia Tech, Lab 4, bar magnets. Purpose of this lab was to measure the distance dependence of the magnetic field due to a small bar magnet, comparing these experimental measurements with theoretical predictions from the Biot-Savart law. Then, to compute and visualize the magnetic field of a dipole using GlowScript, and then to compute computational predictions with real-life measurements that we took earlier at different orientations. So we use formulas to analytically measure the magnetic field during different points in this lab. So the main formula used is this one below, B, that relates the magnetic field of a dipole with nu, the dipole moment, and r, which is the distance, the distance vector. And then you can simplify that as B on the axis and B on the axis, which is nu over 4 pi times nu over r cube, and B parallel, which is nu over 4 pi times 2 nu over r cube. We also used a simple law that the magnitude of the magnetic field to a bar magnet is k is some constant k times the distance to the power n, and then you can just natural log that to get this expression right here. So the experiment. So in the experiment, we measured different distances of a given magnetic field. The system was the location slash magnetometer. The surrounding was the magnet, and the possible errors were in this experiment could have been the lots of magnetic noise from the room. So from your watch, from your laptop, whatever. Somewhat unreliable magnetometer because it's on the phone. It's not really reliable. Movement due to moving phones. So again, you could just mess up magnetometer readings due to moving the phone, or just measurement errors like parallax. So the experiment. So the data can be seen on the left. That is a different distance versus the magnetic field measurements that we got through the experiment, and then the average was taken for the blue boxes, and then those average were then used as the average R and the average B, and then using our previous relation of linear regression, we actually plotted this on a graph using the natural log of R and natural log of B of x, B the magnetic field along the x-axis, and on the slope of this line, the line of best fit, is negative 0.931, which corresponds to n in the previous equation of the magnitude of a bar magnet in this one. So the value of n in this expression would be negative 0.91, and this is the expression we use to get this graph. So GlowScript simulation. So because n is not equal to 3, which is the ideal value of n for a dipole, there will be discrepancy. So yeah, and this is how we used to calculate the b using this equation in the GlowScript model. And this is the GlowScript simulation. So we have defined different vectors to actually see it when we run the simulation, and sorry, and we visualize the magnetic field by calculating dperp and dperpendicular. Sorry, so you can have a look at that here. And our final results include uh, our D, the distance average was 0.39, and our dperp was 0.27, and our Bx was this. These are all in microteslas, by the way. The magnetic field measurements. B was corrected for, and this was the final value, and then the final B net was 62.7 microteslas. So when we ran the simulation, though, we got this result. So comparing the two, you can see they're pretty different B field vectors, but they're within the same order of magnitude. And this can be easily explained by sources of error that we discussed earlier. And the n experimental value was not negative 3, was not 3, so it obviously would differ from the ideal dipole. What if you had an orientated experiment compensated for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How the results have changed? So there'd be much more increased error due to Earth's magnetic pole, so you could not easily remove Earth's magnetic field since this field would contribute to both the x and y components of the B field. This could be avoided if you knew what intermediate angle we were recording at, but that would require much more work at trigonometry that would not be needed. So we would have to consider z component of B field now, which would add more complexity. So yeah, that's how our results would have changed. What if you were to stick two identical magnets together end to end and run the experiment again? How would your experiment measurements differ? Two magnets is greater magnetic field, so nu would increase. And in theory, if you assume an ideal dipole, and if it's identical, it would actually increase by double. So distances for each recorded t value would increase significantly due to the increased magnetic field. That's all. Thank you so much. This is Thomas Shukla for Lab 4, signing off.